let's get started, please. Welcome to the second half of the course. Time flies. This is lecture 5, and this week we are going to be talking about graphs and some other random stuff that we're jamming into Thursday's lecture. But for now, we're just going to talk about graphs. So, graphs are a data structure or a data type that allow us to represent connections or relationships between things. And we already saw trees last week. So we had the hierarchical structure, we had the general and the whatever it was, colonels, the captains, the sergeants. So that was a hierarchical structure where you had something on top and then the next one, then the next one. But that's just a very specific type of relationship. You might have just generally relationships between things that are not hierarchical. So friends on Facebook, followers on Twitter, connections between machines on the internet, flights, etc., etc. So we're going to have a bunch of terminology we need to introduce. So a graph consists of a bunch of vertices or nodes. Vertices and nodes are the same thing for our purposes. And edges. And edges are simply pairs of vertices that are connected to each other. So I'll just scroll up for a second. We're using this Python package called NetworkX for all the graph stuff. And so that's what NX refers to. You should be able to install this with pip, hopefully. So here's what I'm doing. I'm creating a graph, nx.graph, and then I'm just adding 5 nodes. I'm naming them A, B, C, D, and E. And now I'm adding edges. So notice again that an edge is a pair of nodes. I'm saying there's an edge between A and B, an edge between B and C. I run this code. And then NetworkX allows me to draw the graph. Come on. OK. Well, let's ignore that one. Allows us to draw the graph. And so here's what we had. We had 5 nodes, A, B, C, D, and E. And those lines are the edges we created. So there's an edge between A and B. That's why I drew a line there. There's an edge between B and C, etc. But there is no edge between B and E. So if we had added an edge between B and E, there would be like a line wrapping around here. B and E are connected because there is a path to get from B to E. There's a path, for example, going through the middle, but there's not an edge between them. They're not directly connected. OK, so some more terminology. The degree of a vertex is the number of neighbors or the number of edges connected to it. So this one at the top, B, has degree 3 because there's 3 edges coming out of it, whereas C has degree 4. A graph is complete if every pair of vertices is joined by an edge. Yeah, Brendan? Yeah.
Can we dim the ones by the projector so we can read the letters a little better?
Yes. I usually don't like to do that, but I will make a temporary exception while we're looking at these small letters. Can you see them?
A little bit.
Yeah. I think they're just too small. Let me instead just draw it on the board. I think that'd be better. OK. Sorry about that. So yes, B has degree 3. 1, 2, 3 neighbors, and C has degree 4, 1, 2, 3, 4 neighbors. So yeah, a graph is complete if there's every possible edge basically is in the graph. So this graph is not complete because, as I said, there's no edge from B to E, and there's no edge from D to A. OK. So this is an example of a complete graph with 4 vertices. Every possible node is connected to every other node with an edge. Questions so far? Yeah, Tom.
Does order between the relationships matter, or is it like a two-way?
We will get there. So the question is there a directionality to the edges? And the answer is we will get there. Okay. So yes, we will talk about this next week. That's fine. So more terminology. A graph is connected if there's a path between any pair of nodes. So this graph is connected because you can get from anywhere to anywhere, even if not directly. There's still a path. But here's a graph that's not connected. It has some stuff over here, some stuff over there, but there's no edge connecting those two groups, and so you can't actually get from anywhere to anywhere in this graph. Okay, now we'll get to Tom's question. So what we've been talking about so far is called an undirected graph because there's no directionality to these edges. So an example of that could be like Facebook. If the nodes are people on Facebook and the edges are friendships, then if I'm friends with you, you're friends with me. There's no one-way friendships on Facebook. Unlike, say, Twitter, where you have followers, where A can follow B, but that doesn't mean B is following A back. So if you were going to represent Twitter, where the nodes were people and the edges were following, then you would want to use a directed graph, which is the next thing we're going to talk about. So in the network X package in Python, we use digraph, directed graph. And again, I can just make one up. And here's an example. So I realize you can't necessarily see the letters, but we have something at the top, which happens to be A, pointing to the thing at the left, which happens to be C. And you can see that it's drawing an arrow there to represent the directionality of the relationship. So maybe this is a Twitter user with 2 followers or something like that. So we can also reverse the direction of this bottom edge. So I'll just make a new graph where the bottom edge is reversed. And now it looks totally different. So it's a different structure of a graph. Now one person's following another person, and that person's following another person. So by reversing the direction of one of those edges, you actually get a different graph, whereas with the undirected graphs, there was no notion of reversing an edge. Questions or comments? Yeah, Tani.
In the code, what's the difference between directed and not directed?
This part.
Okay.
So it's just a different class. So this graph is undirected graph and digraph is directed graph. Okay, so here's another example of a directed graph. This is a somewhat outdated MDS prerequisite chart throughout all the courses. And so this is going to be directed because we're saying this requires that, and this requires that, and this requires that. And it's not necessarily reciprocal relationship. But we talked about trees before. This is not a tree either, because we have, for example, this capstone course at the bottom has multiple parents, which you can't have in a tree. In a tree, node can have multiple children, but not multiple parents. So we're actually representing something that we couldn't have represented before with just trees. Okay. I just want to point out that you can have two-way edges. So here I've added an edge from C to A and an edge from A to C. That would have been redundant in an undirected graph, but it's not redundant in a directed graph. And that's getting drawn with this double-headed arrow at the bottom edge. So this graph has 3 directed edges. One of them is being drawn as this double-headed arrow. Okay, we're not really going to go into this in this course, but with directed graphs, you can also have self-connections, like an edge from a node to itself. I think what I said, I think network X will not actually draw those properly, so if you try it, it won't even look right. But anyways, I don't think we really need those for this course, but we will need them later on in the program. So these will be coming back. Okay, next thing about graph type. So all these graphs are unweighted graphs because all the edges are the same. So these edges, they're all just edges. And even if they're directed, every directed edge is just a directed edge. But a very common thing you may want when you're using a graph to model a problem and then solve the problem is weighted edges. So here's the code. I'm just putting a weight on these edges. The edge from A to B has a weight of 2. The other one has a weight of 5, etc. And when I draw this, it's just, this is an undirected weighted graph where now somehow this edge on the right is somehow stronger or more important than the other edges. And what that really means is going to depend on the problem we're solving, and I'll give you some examples in a minute. But let me just show you a directed version of that. So here's a directed version, same kind of thing. So here's some examples. Flights between airports. So you could imagine modeling all the possible airports as nodes and the direct flights as directed edges. And then someone goes into Google or whatever and they say, I want to fly from Vancouver to some faraway place. And it's going to say, OK, what's the best way to get there? It's going to use a type of algorithm that we're going to talk about in this course. And so there's maybe not a direct flight to where you're trying to go. So now it says, OK, should I take this path connecting through one city, or should I take this path connecting through another city? Well, how do I compare two paths to say which is the better flight? Well, the user is going to decide. Maybe they want the cheapest flight. So in that case, you could think of the weights on all these edges as the cost of the ticket. So flying from Vancouver to Toronto is $500, then that weight is $500. Flying from Vancouver to Beijing is $1,000. That's the weight of 1,000 on that, et cetera, et cetera. And then what you're actually going to want to find is the path from Vancouver to wherever you're trying to go with the lowest total weight. And there are graph algorithms to solve that. But you need the weights to actually model the problem properly, because you're not just trying to minimize the number of flights that you're taking, but actually you want to minimize maybe the total cost or maybe the total duration, et cetera, et cetera. And of course, it's a bit more complicated with layovers and all that kind of stuff, but I'm just trying to give you an idea of why you might want weighted edges. So yeah, you can look into the shortest path problem. It's a famous graph problem that is pretty much the one I just described. Just a second, Mohammed. And another example would be countries. So maybe you're modeling countries as nodes, and you have some relationships between countries, like number of dual citizens or the amount of trade between them. And these might be directed. So there's trade, export in one direction, then import in the other direction. So you may actually have two directed edges going back and forth between two countries with different weights. And then maybe you want to do something to that graph to solve a problem or answer a question that you're trying to answer. Mohammed.
Can you have two weights for an edge, each for each direction?
Yes. So you can have between me and you an edge in this direction, edge in that direction with different weights. That's fine. Ryan.
Does it make sense to have weighted nodes in any situation?
Does it make sense to have weighted nodes? Whew. That has probably come up at some point, but it is a lot less standard. Yeah, it's not like an obvious common thing like weighted edges is, but I'm sure it's been done. Any other questions? Okay, so now we need to take a digression that will seemingly have nothing to do with what we just talked about, but we're going to use it in about 10 minutes, so we just need to do this digression. So I just wanted to talk about two data structures that will show up in a classic algorithms and data structures course at your neighborhood university. And these are called stacks and queues. So the idea of a stack is it's like a stack of plates on your table or a stack of books on your desk that you have your table, you put a book on on top of it, and then you have another book, and so you put your another book on top of that, and then another friend lends you their, I don't know, algorithms textbook that's really big, and you put it on top of that, and now you say, actually, I would like to now retrieve something from my stack, and what it works is you just take whatever book is at the top of your stack. So it's really like the English word stack. So basically, this data structure just has two operations. You can put something on it, often called push, and you can take something off of it, often called pop. And so I have just implemented this using a list, so it's not very exciting. You just make a stack, it creates an empty list. If I want to put something on it, I stick it at the end of the list. And if I want to take something off of it, the Python list apparently already has a function called pop, which just takes the thing at the beginning, returns it, and then removes that thing from the list. So I guess I didn't really need this stack data type because the list would just do the job, but that's fine. And then I made an isEmpty function that just checks if it's empty or not. OK, so I guess a list would have done the job. But anyways, I have a stack. I can put something on it. So got to run the cell. OK, so I put on first and second. Might be too small for some of you to read, but I put on first and second, and then I run pop. And so that's going to return to me second. And now when I print the stack again, I had actually taken this off the stack. And then I push on third and fourth. Now it has first, third, and fourth. And then I can pop things off the end. I got the fourth thing, I got the third thing, I got the first thing, and now I just have an error because there was nothing left in my stack. So just scrolling up for a second, you may see this last in, first out. So that just means the last thing you put on top of the stack is the first thing you take off the stack. James.
See, should that pop or a stack change the first out of the
Sorry, yes. Thank you for pointing that out. It would, conceptually, what I should have said is that push puts something on the end and pop takes it off the end. Thank you for clarifying that. I just misspoke. OK. And then the queue is basically the opposite of that. So the queue is, you could think about it as there's an office at the motor vehicle branch or whatever you're trying to renew your driver's license, and there's a lineup of people. So the first person shows up, they go into the queue. The second person shows up, they go to the back of the line, and then finally, after an hour or two, they're ready to process the next driver's license application. So the person at the front of the line gets served next. So just like a queue, and again, the English word queue. And so that's first in, first out, meaning the first person to show up there is the first person that is served. Or in this case, I'm just going to use push and pop again to align it with the stack. So the only difference between this and the code above is that here I'm just popping something off the beginning of the queue. So I'm taking the first person, whereas with the stack I was popping something off the end. Thank you, James. I was taking the last book that I had put on. So other than that, they're exactly the same. And I could show an example. So I put on first and second. By the way, there's these other words, unqueue and dequeue, which are sometimes used instead of push and pop. It doesn't really matter. The point is that with the stack, I would have popped off second because that was the most recent thing I put in there. But because this is now a queue, I'm going to pop off first because that was the first thing that was put into the queue. And if I print queue, that person has renewed their driver's license. They're not in the queue anymore. Now the third and fourth people show up, and they all get served in the order they arrived. So stack and queue, two simple data structures that are kind of like lists. They hold things. except that with the list, you can just grab any element you want at any time, x5, x7, x0. But with a stack, you have to get the most recent thing, and with a queue, you have to get the least recent thing. Any questions about that? Again, the relevance to graphs is forthcoming soon. Okay. Graph searches. So this is kind of the meat of today's class. So yeah, we talked about graphs, we made graphs, we looked at graphs, but we actually want to do algorithms on the graph data structure. So we can do things like find the best set of flights to get from A to B that is cheapest or fastest or whatever. Okay, so here's a graph. I think I'm going to have to zoom in here temporarily. Sorry. I bet there's a way to make the font bigger that I'll have to figure out later. Okay, so here's a zoomed in version. And the question is, are nodes 0 and node 14 connected? So maybe you just want to say, well, is there even any way for me to fly from here to there? I mean, these days there often is, but maybe you have a network of roads or something like that. Or maybe it's Facebook and you have two people and you want to say, are we connected at all? Are you my friend as many times as you want to do that? Or are we just completely in different social networks with no friendships bridging those two social networks? So that's the question we're trying to answer. Does there exist a path from node A to node B? So we can just look at this and say, well, node 0 to node 14, yeah, there's a path. We can just eyeball it, and we can see that node 3 is a common friend. But we need an algorithm to do this, because if we have Facebook with 1 billion nodes, we can't just eyeball it. Or if we have a huge network of a transportation, shipping network, whatever, we can't just eyeball it once the data set becomes too big. That's why we want algorithms. So that is the question we're going to focus on trying to answer for the next 20 minutes or so. Given a graph and given two nodes of interest, are they connected? Questions about the goal? Okay. Back to 175% land. Oh, gosh, too much changing of lights. Okay. Okay, so here's what we're going to do. Here's our approach. We're going to start at one of the two nodes. We'll call it the start node and the end node, or the start node and the goal node, or whatever. Yes, some people didn't like the change of lighting. Tani, sorry. And what we're going to do is we're just going to start at node 0 and just take the neighbors of node 0. So, and then we're going to take the neighbors we're going to take one of the neighbors of node 0, and we're going to say, well, let's look at the neighbors of that person. So essentially, our general strategy is going to be just keep taking neighbors of neighbors of neighbors of neighbors of neighbors, and just hope we get there at some point. And if we never get there, then they're not connected. However, that code might get in an infinite loop. If I started with A and I said, I'm looking for C, and I said, oh, neighbor, 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 I'll just be going around and around and around, and my code will never terminate. And so the other thing I need to do is I just need to keep track of which nodes I have visited. So if I have already visited node B, I'm just going to write that down and say I've already visited node B. Don't come back to node B. So that's fine. But if I go from A to B, and then I mark B as visited, and then I go from B to D, well, maybe I'm in this type of situation where actually the only way to get where I'm going to C is through B. So I cannot just forget about this relationship. I cannot just say I've gone from A to B, I've gone from B to D. Now I'll never go back to B ever again, because if I do that, well, I will never get where I'm trying to go. So I want to mark something as visited when I visit it so that I do not go around and around and around and around. But as soon as I visit something, I also want to write down all of its neighbors and just keep track of them somewhere. because I don't want to, at some point I should explore going in that direction. Okay, so I'm going to show you a few pieces of code that correctly solve the problem of whether two nodes are connected, and then we're going to discuss them in detail. So here's the first one. Def connected, it takes in a graph G, which is a network X graph data type. It takes in the two nodes we're interested in. Let's just ignore these other arguments for now. It returns a Boolean, that makes sense. True if they're connected, false if they're not connected. And here's how it works. Here's this thing that I told you about that just checks if things have been visited or not. So we're going to use a set, a Python set, because that's a good data structure for this. We just want to put stuff in it that we visited, and we want to check if something is in there to see have we already visited that. And like we talked about last week, a set, that's exactly what sets do. You put stuff in them, and then you check if stuff is in them. So that's why we're using a set. So if this is my first time and visited is none, I'm just going to make visited a Python set with node 1 in it, because I'm starting at node 1. And just conceptually, we're going to start at node 1 and try to get to node 2. So, but if you switch the order, it wouldn't matter, because this is an undirected graph for now. But if you had a directed graph, then it might actually matter. OK, so here's my set. Now this is going to be a recursive function. So here's my base case, which is if node 1 equals node 2. So node 1 is kind of going to be like our current node. We're going to be traveling around node 1, node 1, node 1, node 1. And node 2 is going to be this place we're trying to get to. So if I eventually get there, then I got there. So I'm going to return true. They must be connected because I just found a way to get there. OK. And now, here's what I'm going to do. I'm going to look at all the neighbors of node 1. So this is where I'm at right now. Say I'm at A. I'm going to look at all the neighbors, B and E. I'm going to loop through them. And for each neighbor, first of all, I'm going to check if it's already been visited. I don't remember if we talked about continue in 5.11 or not, but in case we didn't, continue just means go to the next cycle of the loop. Do not execute the rest of the things that I'm supposed to do in the loop, but just go to the next one. So for V in the neighbors of node 1, if V in visited continue, basically just means for V in the unvisited neighbors of node 1. Because if you pick a visited one, it just immediately skips that iteration of the loop. OK, so for all the unvisited neighbors of node 1, first, for a particular neighbor that I'm dealing with, so A has two neighbors, B and E, I'm going to start with B if they're ordered alphabetically. First, I'm just going to mark down that that's been visited, because that has now been, well, visited. And then this is just for printing stuff out. We can ignore that. And here's the recursive call. Now I'm going to say call connected recursively, but now with this neighbor V as node 1. So basically what this is saying, the recursion is saying, is that if any of my neighbors are connected to node 2, then I'm connected to node 2, because I'm connected to all my neighbors. That's the definition of neighbor. So if you're trying to get from A to C, it's saying, well, I have two neighbors. Are any of them connected to C? And then it's going to recursively look at the neighbors of those things and those things. And if you ever get there, it's going to immediately return true. And if you get all the way to the end of all this recursion, and you get to the end of the entire function, and you never actually found anything, and everything has been visited, so there's no more looping to be done anymore, then it's going to return false. Andy.
Neighbors is also a set? I don't think we actually saw.
Neighbors is a network X function. It's a method of the graph class, and you give it a node in the graph, and it gives you, I don't know if it's a set or a list or something that you can iterate through containing the neighbors of that node in that specific graph. Any other questions? You.
Can you explain again for all the unvisited neighbors of node 1?
Yes, can I explain that again? So I was just, these 3 lines of code, what they really say is for all the neighbors, but then immediately inside the loop, well, if that neighbor has already been visited, just skip. And so I try to condense that into a shorter, like, English phrase, which is really for all the unvisited neighbors. Because for all the neighbors, but not the ones that are visited, is basically the same as for all the unvisited neighbors. So, for example, if you are starting at A, now A is visited, and now you go to B, and now B is visited. Well, what are all the neighbors of B? They're A, C, and D. But I don't want to go back to A because I've already been there. So what's going to happen is, well, A is one of the neighbors of B, but it's going to trigger that continue statement. It's going to say, oh, but A is already visited, so just skip. And so conceptually, what we're really doing is just taking the unvisited neighbors of B, which are C and D. Alistair.
Are you using a stack in this?
I'm about to use a stack, but not yet. So this is the recursive implementation. Then we're going to look at the not recursive implementation, and then we will get our stacks and queues. Gaurav.
What is verbose here?
Louder, please.
What is verbose here?
Oh, verbose, yeah. So it's just fairly common when you're programming to allow the person using your function to decide how much stuff they want you to print to the screen, because it can sometimes be annoying when your function prints stuff. So you want to let the person disable it if they want to, but sometimes you like to be able to print stuff. So a pretty common pattern in all programming languages is you'll just have an argument called verbose. And if it's true, it means your function can print out all kinds of stuff. And if it's false, it means please don't print stuff out because that's annoying. And so then I just have if verbose print stuff out. And so by default, it'll print nothing. But you can turn that on and just see how it's traversing all the nodes in the graph. Sam.
In our example on the board, do we visit E twice? Because we would check it over the...
In our example on the board, do we visit E twice? So no, we don't visit anything twice. We might visit E because it's a neighbor of A, or we might visit E in this direction. And we will talk very soon about which order things get visited in. But one way or the other, E is going to get visited first. And then the second time it gets there, it's just going to skip it. And so that way, like if E had a bunch of neighbors, you would only be exploring this part of the graph one time. Yeah, Mohammed.
So in the recursive function, every time V will be updated with the new node?
Yes. Well, in the recursive function, every time node 1 will become the new node. Because if you look at how I'm calling connected, I'm replacing node 1 with V. So it's saying, instead of getting from A to C, I actually want to get from A's neighbor to C. And then A's neighbor's neighbors to C, and so on. So yeah, node 2 is staying the same, but I'm replacing the start node every time. Okay, let's run the code. I think we discussed how the code works. Let's run the code. Okay, so first of all, from that graph we showed before, is node 0 and node 14 connected? True. Well, actually, that graph is not very interesting because everything is connected to everything else. If I just scroll back up. So speaking of writing good tests, this would be a bad graph to test that function we just wrote because every node is connected to every other node. So just writing a function that said return true would pass all the tests if you were only testing on this graph. So we need a better graph so we can do some more meaningful testing. Scrolling down. So here's a graph that we can test on. So now these two at the bottom, for those who can't see, are E and F. So E and F should not be connected to A, B, C, and D. A, B, C, and D are at the top, E and F are at the bottom. So I just want to make sure all these things are connected, and I want to make sure all these things are not connected, and everything seems to be okay. So the code seems to work. But now going back to what Sam brought up, well, in what order are the nodes traversed? So that's where I can use our friend verbose that we just talked about. So I can actually turn on verbose, and I can see the order that the nodes were traversed, but I guess this is more or less useless because you can't actually see the numbers because they're too small on the graph. So you can look at this later, but I will just tell you what's happening, which is that it is, say we're starting with A. It's going to take all the neighbors of A, and then it's just going to go with one of them. So it's going to go from A to B. And now we're inside of that recursive call where node 1 is actually B. So now it's going to take all the neighbors of B, and let's say the neighbors are sorted alphabetically in network X. Then it's going to take all the neighbors of B, and C is the first one, so it's going to go to C. And maybe now we're done, but if we weren't done, it would exit the recursion and then take the next neighbor of B, which is D, and then it would look at the neighbors of D, and so on. So what it's basically doing is it's going to the neighbors, 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 because recursing inside. And so if you had something else, like Z would not actually be touched until much, much, much later, because all this other stuff would have to finish before we said, well, what about the second neighbor of A? Annie?
In these examples, it's all letters and numbers, and it always seems to be going in order, like I said, numbers are alphabetically. So is that always the case, or do you have to write that in?
Yeah, so the question was, in these examples, the nodes are labeled with letters or numbers, and so then we have some sort of ordering. Is that always the case? So the ordering is not important for the code to work, so the code's going to work regardless. I'm just bringing up the ordering because this, scrolling up here, this function g.neighbors, I believe just the people who made network X, they're going to give you the neighbors in order. And so that just happens to be like ascending order for integers or for strings. But if you just had nodes with some weird labels, it wouldn't matter. It would just give them to you in some arbitrary order. But just for the purposes of talking about how the code works, it's kind of convenient that we know what order g.neighbors is feeding them to us, because then we can really step through the code and see what it's doing. And I haven't really yet told you why we even care what order it's traversing the nodes, because, hey, if connected gets the job done, that should be good enough. But I will talk about that in a minute. Forgot your name.
Zachariah.
Zachariah, right.
The shortest route could be like 0314. Can we make it like 2?
Aha, yes. You would like to take the shortest route, and you're upset that it's taking a ridiculously long route instead. So, yeah, we will talk about that. Just hold on to that for a minute. Braden.
Would the current node ever check the neighbors, like multiple neighbors simultaneously?
Well, there is no simultaneously. I mean, it's code. It has to do one thing at a time. So it could check, is this where I'm trying to go? Is this where I'm trying to go? Is this where I'm trying to go? It could check all the neighbors of A before moving on to the neighbors of neighbors. But at the end of the day, it has to do one thing at a time. Okay, so this may not be possible while you're sitting there watching the lecture, but it would be worth going back to this later and just thinking about this recursion and the order that it prints out, and try to understand why it's visiting the nodes in the order that it's visiting the nodes. Okay, so I'm not going to go through all this right now because it's too small to read. Okay, so next thing we're going to do is talk about the not recursive implementation using stacks and queues. but just looking at the time, I think we should take a break now. So it's 10:10. Let's resume at 10:15, and we'll talk about more of this. During the break, Serg showed me how to make the graph a bit more readable by changing the font size and color. It's a bit late, but anyways, better late than never. Someone also asked, like, what is this graph? It has a funny name, as you'll see when I create it. It's just, I looked through all the graphs that were built into Network X, like pre-packaged examples, and it just seemed like a good example. There's nothing more to it than that. So I just picked one of the many examples that were built into the package. Okay, so let's move on. Okay, graph searches, iterative implementation. So we just talked about the recursive one. Let's now implement it non-recursively. So here's what we're going to do. Every time we visit a node, we are going to mark it as visited, same as before, but we are going to take all of its neighbors and we are going to add them to a queue. So we just talked about stacks and queues before. So remember how I talked about, well, when we go to a node, we need to remember what all its neighbors are before moving on. So recursively, there was basically the function call stack that was kind of remembering what the heck was going on here. Like, this function called itself, and then it just remembered when it's done this, go back to the function that called it and get the other neighbor. And at the end of the day, you had like a whole bunch of recursive calls within each other. Each one was stuck at a different line of code, and then you kind of came back to it, remembered where you were, and kept going. But when we're doing it iteratively with a loop, we're not doing it recursively. We need to explicitly store the neighbors. And so here's what we're going to do. We're going to make a queue. We're going to put node 1 in the queue. We're going to make our visited set the same as before. And now our loop is going to be while the queue is not empty. So as long as there's more neighbors that we haven't looked at yet, just keep on looking for node 2. And now what we're going to do is we're going to pop the thing at the beginning of the queue. So we're going to get one of these nodes. And right now, we just put node 1 in the queue, so that was the only thing in the queue. So that's going to be node 1 that gets popped off. If the thing that we're working on, so I should have been more consistent. Oh well. Anyways, if that thing is node 2, then we're done. We found it. Hey, we found node 2. Same as the recursive thing, we return true. And same as before, if that thing was visited, then, well, it's visited, so we don't want to pursue it any further. And now I'm going to add it to the list of visited things. So if we're starting with A has now been visited. And then this is the entire rest of the function. The entire rest of the function just says, take all of the neighbors of the current vertex and stick them in the queue. So how is that going to work? Well, if we start with A and we're looking for C, we're going to mark A as visited. So first the queue had A in it. Here's the driver's license renewal window. Now we had A in it, waiting in line. And then we have the neighbors of A, which are going to, so A is going to actually get popped off the queue, and we're going to take the neighbors B, E, and Z. So A has been served, and then we're going to take B, E, and Z and put them in the lineup. And then we're going to say, okay, who's next? Q.pop. Well, B is next, so we're going to mark B as visited. And we're going to say, is B the thing we're looking for? Let's say it's not. Let's say C is the thing we're looking for. Is B the thing we're looking for? No. So we have to keep going. Okay, well, let me put all the neighbors of B onto the queue, which are A, C, and D. So I guess maybe an even less confusing implementation would be if v not in. We don't even really need to bother adding a to the queue because we've already visited a. So let's make that minor simplification. So all the neighbors of b are a, c, and d, but a has already been visited, so let's forget about that. Let's put c and d in the queue, and b has been dealt with. And then we're going to go to the next thing in line, which is e. And e actually, how did I get e on there? Oh, from a, right. So e has neighbors a that's already been visited, and d is already on the queue. Ugh. Sorry, we could make more simplifications. So we might as well not add something to the queue that's already in the queue as well. So we could simplify that as well. Anyways, you will keep going, and eventually you're going to get to you're going to get to C, and then you're going to say, well, that's what I was looking for. So it doesn't really matter. The code is going to work either way. It's just a bit weirder to explain it conceptually this way. Okay. And so then we can run the code, and it works, and we can do all of the other tests. So what I want to get to is that that thing I just showed you is called breadth first search. And there's another thing. The recursive one I showed you earlier is called depth first search. And the difference between them was the order that they looked at the nodes. So depth first search basically just goes as deep as possible first, which is what recursion does. It says, let me first go to my first neighbors, first neighbors, first neighbors, first neighbors, first neighbor. Oh, that's not it. Then let me go to their second neighbor. Oh, that's not it. And so on. So it's going all the way down the depth of the neighborhood relationship, whereas breadth first search is saying, let me look at all my neighbors. Oh, none of them are it. Okay, let me look at all their neighbors. Oh, none of them are it. Oh, let me look at all their neighbors. And the beauty of this, the idea here is that all I actually need to do to change it from breadth first search to depth first search is change this queue to a stack. Because we talked about stacks and queues earlier. Do I go from the beginning? Do I go from the end? As soon as I change this queue to the stack, the code still works, but we've changed our algorithm from breadth first search to depth first search. And this one with the stack is now pretty much the same thing as the recursive code we talked before. And why is that? Well, because I'm putting everything on a stack. I'm putting my neighbors on a stack, but then I'm popping off the most recent thing, the end on the line. That's going to be the neighbors I just put on the stack. And then I'm going to go to that person, look at all their neighbors, and put them on the stack. But then I'm going to get the most recent thing, which was those neighbors I just added. And so you kind of go down the neighbor, neighbor, neighbor rabbit hole with depth first search, whereas with breadth first search, you kind of look at closer by things. So by this point, you would be well within your rights to wonder, why would you possibly care which order you're going to traverse the nodes in, because both of these things work, right? Both of them look through everything. They don't get in infinite loops because we're checking if they're visited. They find the stuff. However, there's going to be certain cases where the code could be much, much faster if you appropriately pick between depth first search and breadth first search. And I mean, someone asked earlier, well, the node I'm looking for is right nearby. So first of all, if you happen to know that they're probably right nearby, then breadth first search is probably going to be faster because it's searching nearby stuff. But in the lab, there's an optional question which asks a slightly different question, not just are these two nodes connected, but what is their degree of separation between them? So how many hops do I have to go to get from this person to that person? So me and Sarah go on Facebook, how many friends of friends of friends do we have to go to see how connected we are? And in that case, there's actually a very nice algorithm similar to breadth first search that's going to do a good job of computing that. So for the purposes of checking where two things are connected, they're both going to work, but it's important to know about both algorithms because sometimes one is going to make more sense than the other. Forget your name.
Elliot.
Elliot.
Yeah, it makes sense intuitively why breadth first search would work better in some situations. What's an example where depth first would?
Yeah, the question was, it makes sense intuitively why breadth first search would make sense in some situations. What's an example of where depth first search would make sense? Gosh, I have to think about that. Let me get back to you. Yeah, there, I will do so. The recursive case is also depth first, but let me think of some good examples.
So how about if the connector dot that target is very deep in the levels, but there's a lot of neighbors in the upper levels?
Yeah, so if you happen to know that the node you're looking for is somehow very far away and there's just a bunch of stuff around the start node, then it would be faster. But I want to try to think of a case where like that would actually happen, like where you would know that. I will come up with something. Yeah. Oh, Annie.
Like when you're on Amazon and you have all those little items that are add-on items, so they're not like just like the thing that you would
Uh-huh.
need an example of that because you're like juicing down like to the down a rabbit hole to the path of something that's very small and it's an add-on item.
The question was add-on items for Amazon. Would that be an example of depth? I'm not sure. The thing is, it's not really a question of whether the item is big or small. The depth is basically saying how far away are you going to go from where you started searching, versus are you going to search, friends and friends of friends first. So I don't know. I don't see the connection. Yeah. Okay, so these things are good to know about. A lot of graph algorithms are just kind of variants on these two things. Maybe not, breadth first search with a few changes or depth first search with a few changes. So it's good to know about them, and the idea that they're pretty much the exact same algorithm, but you're just switching the stack and the queue. You're just switching, do I look at the most recent things first or the least recent things first, is a nice idea in algorithms and data structures. Let's move on. The next thing we're going to talk about is this idea of centrality. So here's a directed graph. Okay, here's where we really want to do that thing that we talked about. Node color equals pink, font size equals 15, or maybe 20. What? Oh, 20. Okay, so here's a graph, and the motivation for this thing is going to be Google PageRank. So Google PageRank is the algorithm that Google was kind of built on. You search for a bunch of web pages, and it had to give you things that were relevant given your keywords, but also important web pages. So if there was something that really well matched your keyword, but was at some dark corner of the internet that nobody cared about, they didn't want to make that your first result. So what they did is they thought about web pages as a graph. So directed graph, where each node is a web page. So you have web page 1, 2, 3, 4, 5. And the directed edges are links. So if I link to your site, that is a directed edge from me to you. And they built this notion of important web pages around sites that have a lot of links to them. So if 1 million people are linking to my website, then my website must be important. That's basically the idea. And so here it is as a graph. So this is part of a more general idea of centrality, of what are the important nodes in the graph. But we don't have time to go into all the different properties of graphs one could talk about, so we're just going to focus on PageRank as a particular example, because I think it's a really nice application of graphs. Okay, so here's the way PageRank works. The websites are nodes in the graph. We talked about this. We put a directed edge from A to B if A links to B. And there's a specific kind of mathematically elegant way of computing PageRank that worked really well for Google. That's not what we're going to go into this course, but we're going to talk about the kind of conceptual simulation of the idea behind PageRank, which is this. You have some web surfer who just picks a random web page that they start on. And what I'm going to do as this random web surfer is I'm just going to click on links. So I'm at the Wikipedia article on elephants. It links to, I don't know, animals. So now I'm going to go to the Wikipedia article on animals. And then that goes to some other website. I'm going to click on that link. So I'm just randomly clicking on links with equal probability of all the links on my page. But then once in a while, after 20 links, I'm just going to go to a completely random web page on the entire internet. So that's basically saying I got bored of what I was doing, and I'm just going to go to some new page on the internet that has nothing necessarily to do with what I was just doing. So mathematically, we start at a random node. With probability alpha, we choose a completely random node. That's the thing I just talked about, me going to a new web page. And with the other probability, 1 minus alpha, I'm going to choose a random neighbor of the current node, meaning I'm going to click on a random link from the page I'm at. And then I'm just going to do this over and over and over and over again. And whatever page I end up on, that is somehow a more important web page. And then we can actually simulate this and try to simulate PageRank. So again, this is not how Google does it, but this is how we're going to do it. So here's my function, PageRank, takes in a graph and this alpha parameter. And at this point, you should be able to understand the code more or less. So we talked about counters a little bit. Those are those fancy default dicts that just count things. I'm going to randomly pick a node to start at. These are just some network X functions I'm using. And then I'm just going to iterate for a certain number of iterations. With probability alpha, I'm going to go to a completely random node. And else, meaning with probability 1 minus alpha, I'm going to go to a random neighbor. This code is a little gross, but g.neighbors we saw earlier. So get all the neighbors of the current node. Turns out I have to turn this into a list in order to call choice on it. Then I call numpy.random.choice. That gives me one of the neighbors. Now that's my current node. And then I just +1 it because I visited it and do this a bunch of times. So I can run this code. And I can look at the things with the highest page. So this 43,000 just means in my simulation it got visited 43,000 times. The number is not that important, but the rank is important. So that website number 2 seems to be the most important website, and then website 0, and then website 1. Oh gosh, I got to. Sorry, 1 second. I'm going to need this again. Come on. What do I do? Okay, so here's what's interesting about this. Just looking at this picture, it kind of seems reasonable that node 2 is the most important web page. You can just see tons of links linking to that site. So yeah, it makes sense. Node 2 got the highest page rank. But here's where it gets interesting. The second most links coming into it looks like node 1. That website has 4 other websites linking to it. So a naive approach to this is just say, let's count the number of links. Oh, node 1 is the second most important because it has the second most links. But where this is really cool that it goes beyond that is that it's actually picking node 0 to have the second highest page rank. And why is that? That is because node 0, yes, sure, it only has 2 sites linking to it. But one of them is the really important site number 2. And so the fact that node 0 has site number 2 linking to it even though it doesn't have that many sites linking to it in total, it boosts it up so much. And just conceptually with our kind of simulation that we just did, you're bouncing around, but you're spending a lot of time at node 2 because there's so many links to node 2. And when you leave node 2, you're actually going to node 0 every time. So actually node 0 is pretty important. I mean, sometimes you're going to go to a random page from node 2 because there's always that probability of going to a random page. But other than that, you're actually spending tons of time on node 0. And so it's doing something more clever than just saying who has the most links. It's actually saying who has the most links, but actually important links, links coming from other important sites. And it kind of works itself out simultaneously deciding what's important and gives you this PageRank. So I just wanted to show this to you because it's a really nice application of graphs, and we're talking about graphs, and the code is only 10 lines long, and it's fun. Any questions or comments about this? Yeah, Furkan.
Yeah, but you can also say that 0 can be important compared to 2 as well, because 2 is 0, right?
Yeah, so you're saying you might even say 0 is more important than 2? My interpretation of what's happening is that, well, you go to 2 all the time, but then you don't always go to 0, because actually sometimes you go to a random node. And so it seems you're actually spending more time at 2 than at 0 because of that. But yeah, it depends on that alpha parameter. Any other questions? So what I'm really trying to say here is graphs are useful and relevant data structures. Yeah, Sarah.
And I think if we would like to further extend this analogy, this graph would probably have to be weighted with weighted edges.
Yes, you could have weighted edges. I mean, what would they be in terms of the links?
Like quality.
Yeah, if you had some way of deciding how important a link was, then yeah, maybe you could. Like, I don't know, if the link is at the top of the Wikipedia page, maybe people are more likely.
Like a government website, which is gonna.
Well, government website, yeah, that would more be like a weight on the node. And so again, the way Google actually works, it's combining this with how relevant the site is to the search terms that you turn in, because this has nothing to do with the search stuff that you typed in. This is just separately from whatever you're searching, which websites are important, and then it combines this ranking with the search quality. I don't know what it does now, but that's what it did 20 years ago or whenever, when they started. Okay, so we talked about that. This is just saying if you only sort by the number of links, then node 1 actually seems more important, but when you do PageRank, node 0 seems more important. Okay, and we'll skip this optional note. Other graph properties. Okay, so graph theory is like its own entire field, and this is just the tip of the iceberg here that we're talking about. So all I really want to say here is, in case you're interested, here's a bunch of links of things you could look up. And in particular, there's a lot of problems in graph theory that people are interested in solving, because you can often map these problems to real-world situations. So we talked about finding if 2 nodes are connected. So that's a problem in graph theory. Another one is what is the shortest path from A to B, which, like we talked about with the flights example, and that's a solved problem. But then there's a whole bunch of other problems that you can read about with those links that people would love to solve, but they can't. Or any algorithm that people can come up with to solve those other problems would be incredibly slow. And that's this idea of NP completeness. So you may have heard of NP completeness from the media or whatever. That's a topic that we would go into in a more traditional algorithms and data structures course that we just don't have time to talk about in this course. So all I'm really planning to say about this is that when you have different problems that you're trying to solve, people can try to categorize them into how fast they can be solved. And generally, it's like they can be solved in polynomial time, like O of n squared, or exponential time, like 2 to the power of n, and exponential time is like the doom scenario where people basically say, okay, that means we don't know how to solve this problem because exponential time is not really doable in most situations. So that's all I really wanted to say about this. These problems exist, and we're not very good at solving them, and some people think they just can't be solved any faster, and that's the whole P equals NP thing that you may have heard about. So that's all I wanted to say about that.